Yes.
Okay, so let's start for today. In our last lecture, we had done the method of successive approximation for analog to digital conversion. And we saw that in comparison to the method before that, that is, in comparison to the ramp method, it had certain advantages. Like, first of all, it took the same number of steps depending upon the number of bits that are used for the analog to digital conversion. And secondly, it was comparatively a lesser time taking with in comparison to the ramp method. So this is quite a popular method, and if this logic is hardwired, then it will just take as many steps. You can do it very fast, very efficiently, but it would still take as much time as the number of bits in which you are seeking to perform the analog to digital conversion. Now, is there any other method that is faster than this, which can be absolutely immediate? Fortunately, we have such a method, and that is called the method of flash conversion. Okay, flash analog to digital conversion, and we will see that method in today's lecture. I have prepared. I've prepared some workbench here so that I don't have to spend a lot of time drawing, but certainly it's necessary to explain it to you gradually and slowly and construct it so that you understand the nuances. So here I've got certain components which we'll need for our flash circuit, and I'm keeping them here. Now, suppose we have the task of converting within a particular range. First of all, say this is the flash method. Of analog to digital conversion. Suppose we have a range of voltage within which the signal lies, and we wish to digitize this signal at any instant of time. So naturally, we are going to pass it through a sample and a hold, and then the signal will remain locked, it will remain constant. We will perform the process of analog to digital conversion. Now, in the flash method, we don't have the limitations that we had in the ramp method or the successive approximation method. But here now we can do this conversion instantaneously. Okay. Now, how does it work? We will explain this with the help of an example, and this has also been nicely illustrated in the book by Alciator and Histand. However, I'll just explain it to you here so that things are absolutely clear to you. Now, suppose we have a voltage range within which the signal lies. Let's take, I have got a voltage divider here, let's say, and it's going to divide the voltage range into certain parts, 1, 2, 3, 4 parts. So we're going to make use of this. Let's say that we have a signal lying within a voltage range, and say the voltage range is Vmin is the lower limit, and here we have Vmax. Okay. And we have divided this voltage range into four different parts, equal parts. And we have used resistances of the same value for that. And it will be clear to you why we have chosen only four in this example. We could have taken more, but we have chosen to take only four. And this is just to explain to you the concept of analog to digital conversion using the flash method only for 2 bits, not for more, only for 2 bits. It may sound a bit surprising why I'm explaining just for 2 bits at the moment, but I'm sure that it will become clear to you shortly. So this is R. Likewise, we also have, this is also R. So we have got these identical resistances. So we have divided this range, Vmin to Vmax, in four equal parts. We could divide it into 8 equal parts, we could divide it into 16 equal parts, 32 equal parts, and so on. Okay. Now, the purpose of dividing it into equal parts is that we are going to get voltages or potentials at these points, okay, which are in equal increments from the previous one. And we have the signal, and we are going to compare our signal with these voltage levels, and we are going to see which is the level within which this voltage signal lies. So let us take, let's say, so I'm taking a voltage signal, the one which we are interested in digitizing, okay, and we'll adjust this. And we are going to pass this through comparators. So we will take this signal. Let's say this signal is coming from our sensors after the hold sample and hold circuit. Let's say after the signal processing and all that. So we'll just write it as S. And we're going to make comparisons. And for comparisons, I've got here in our workbench, I've got here a component. So I'm just going to take it so that we save some time. So we'll take this. So in the same way, we have a few more comparators. We have another one placed here. So you can see that we are just making these comparisons. We'll have one more. So we have got these different comparators here, and what they are going to do is they are going to compare this signal, which is uh, the analog signal which we are interested in digitizing. So this is our analog input. And these are our comparators. Of course, in order to depict clearly that they are not intersecting, I will just take these dots which have been prepared beforehand. So we have got this uh, set of comparators here, and you can see that if we have, let's say, um, this corresponding to 0 volts here, and the Vmax corresponding to, let's say, just for understanding, 4 volts over here. It's not necessary that we should have 4, but this is just to make things easy. So in that case, we will have 4 minus 0 and divided by these 4, divided by 4R. So that will be, we will have, if we take R as, say, a unit resistance, we can, or an high resistance, okay? Let's take this as, this will become 1 volt. This will become 2 volt. Now what I have written in red is just the example. In general, it need not be like this, okay? So we have got these different voltage levels. So now if our signal is in the range 0 to 1 volts, it will lie, it will be compared over here, and accordingly we will get a high or a low. So let us say that we get, if um, if this is greater, if the value of the signal is greater than the one in the inverting end, then you will get a 1, otherwise you will get a 0. So this is the logic that we will follow. Okay. Now, you see, at some point of time, we have to, this signal is continuously is available at this terminal. And we are interested in digitizing at a particular instant of time. And so we require a trigger. So we will make use of a trigger, and that trigger is actually to work in conjunction with a set of latches. So we will take, I have prepared a latch here, uh, and I'm going to place it here. So this latch is going to be placed here, And we are going to have more of these latches. Another latch here and another here. Okay. So we have got these latches also here, and these latches will provide an output certainly. Um, they will provide an output depending upon the trigger which is provided at the input C. We will show that input C as well now. So let's take another lead for the trigger. So we are going to trigger it um, from here. And so this is our trigger. It's just like a switch, you know. So you can just switch it on. The moment you switch it on, when C gets activated, whatever is the input available on D gets latched here on Q. Okay. So let us also connect this. And these are the outputs. And these outputs from the latches, in fact, we need to also uh, show the connections here. So So we'll take a specific voltage level and we'll try to digitize it as well. But right now, uh, okay, let us take a particular value. Let us say we take a value of a signal. Let's say, as an example, we take 2.4 volts. Okay, just this is an example, 2.4 volts. And we are interested in digitizing this uh, using 2-bit ADC. So our example is for a 2-bit analog to digital based on the flash method. So you can see that uh, our signal lies in this range between 2 and 3. Okay, it lies between 2 and 3. So when you compare here, you will see that 2.4 is greater than 1. So 1 will be activated. Okay, output will be 1. Over here, 2.4 is again greater than 2. So the output will be activated. Okay, here 2.4 is less than 3, and so 0 will be activated. Okay, so you can see that uh, the bit pattern that you get, let's say the bit pattern, the moment you press this trigger, whatever is the bit pattern available here will be latched and made available over here. So if this is say G0, if this is corresponding to G0, this is corresponding to G1, and this to G2, we have possibilities. We have possibilities of values of. So in this particular example, we will have uh, G0 as corresponding to 1, G1 as corresponding to 1, and G2 corresponding to 0. Okay. So now we will take, our job is to convert this into a 2-bit analog to digital uh, value. So for that, we will make use of what we call as a code converter. It is a circuit, and it's a combination logic circuit. So I have got a box already for that, and we'll make use of it. We'll just place it here. So this box is actually just a circuit wherein you have, so we'll just place this here. We are passing in 3 inputs, and we are going to obtain only 2 outputs, and the outputs are going to be uh, say, because they are in only 2 bits, so we'll say B0 and B1. Okay, so what is possible for us? Several values which are possible. Here we may have G, say G0. Here we have G1, and here we have G2. Okay, corresponding to the values, corresponding to the different levels, say either we have zeros, 0, 0, 0, 0. When the level is 0, 0, 0, that is uh, when you have this range over here, and then the signal is in this range, you will get some output. Then you have another possibility, that is 0, 0, 1, then 0, 1, 0, 0, 1, 1. Because you see, G0 and G1 both will be, these will certainly be on. Over here you will have 1, 1, 1. So these are the combinations that are possible. And in our specific example, we are going to have this particular level, 0, 1, 1. So this is our particular, in our particular example. Okay. Now this is going to correspond to, this has to correspond to a particular uh, combination at the output. So here we could take B1 and here B0. So let's say that corresponding to all these as zeros, we have 0, 0, the 2 bits of the ADC. Corresponding to 0, 0, 1, we have 0, 1. Corresponding to this, we have 1, 0. And corresponding to this, we have 1, 1. So you can see now that because our signal, because our circuit is has a combination of the signal level produces this combination of G0, G1, G2, which is marked here. Our output will correspondingly be here, what we have here. Okay, this is what will happen. So this will be our digitized. It will be our digitized analog to digital conversion value. Okay, this will be our ADC value. So this will be the digital representation of the signal. The component which we have here we call as a code converter, and it's just you can see already that it is based on combination logic. So it's just a combination logic circuit. So it's just a combination logic circuit, and this is going to produce output in the form of bits. And in our case, we just have 2 bits. So we could just represent it like this. I'm sorry. So we just have these 2 bits, B0. We can just place so you have the digits here, which is our ADC value. This ADC value is available here. It's this digital representation that we have here. Okay, I think I can erase this part now completely. So I hope this is clear to you. Now comes what should be this combination logic circuit here. Let's say for example, let's take another color. Yeah, so maybe we can take blue itself. Yeah, so we can write the combination logic. You can see the logic for B1, For B1, the logic will be um, the corresponding to the product here. Okay, you will get G2 and G1 and G0. Okay, and or not G2 and G1 and G0. So these two possibilities. This is one. You can of course simplify it. Please simplify it and see for yourself what is the final B1 that you're getting. What is the logic expression that you're getting? Of course, you can simplify it. You can certainly eliminate G2 from this. But perhaps you can go a step further. Just check it and satisfy yourself. Uh, for B2 again, we can have the combination. Sorry, not for B2, for B naught. So for B naught, we can have the combination as G2 and G1 and G naught, or not G2 and not G1 and G naught. Corresponding to this line here. So please simplify this. The task for you is to simplify. I leave this as homework for you. So simplify the Boolean expressions. And you can fill up your circuit here inside this box. So that will be our code converter. Now, what have you achieved in this? You can see that your signal is continuously available here based on the sample and hold. Okay, after the sample and hold. So I'll write it here after the sample and hold. We have the signal analog input available here continuously, and it's in the range of 0 to 4. In this particular case, we may have other voltage ranges here. Now, the moment you press this trigger, the outputs over here get latched. Now you see, you have very limited outputs possible. You have just 4 levels here because you use just 4 levels here. You broke this potential range into 4 equal parts, and you require one less comparator. You require 3 comparators, not 4, and 3 latches. So the moment you press this trigger, the output of these comparators, which is going to be input to the latches, will be available here to the code converter. And the code converter is just a combination logic circuit, and it will immediately provide the analog to digital conversion value. So this happens in a flash. You see, just have to press this trigger and immediately this value is available here. Unlike the earlier techniques where we saw that we were making use of digital to analog conversion, but here we are not making use of digital to analog conversion. So you see, one aspect of this is that we are not using DAC is not used. Okay, this is one aspect. The second aspect is that it's just one shot. You just have to press the trigger and you get the ADC value here. So this is just a instantaneous, you can say immediate, instant conversion. Okay, so it's instant ADC. I'll write it. Instant analog to digital conversion. Okay, there's no faster method than this, and that is the main advantage of this. What are the disadvantages of this method? Can you tell me? Now, do you realize why I have taken only 2 bits here and made only 4 levels for this voltage range? Yes, anyone? Anybody can guess? I hope you're paying attention. Can you all hear me?
Yes, sir.
So, can you guess why I have taken just 4? You can see for yourself that if we take one more bit over here, that means we will require 8 different parts for this range. That means we are going to have 8 resistances and 7 comparators, 7 latches. Okay, that's just for 3 bits. If we take one more bit, that is make it 4 bits, we are going to have 16 resistances here, 15 comparators here, 15 latches here. Okay, and we'll have a combination logic which is required for 4 outputs. Okay, and there will be 15 inputs here, 15 inputs. So you can see that as we go on adding more and more bits, that means as our flash converter becomes more and more of a higher resolution, as the resolution of the flash converter increases, we have to double up the number of resistances and the comparators and latches, and also the logic. Naturally, when you implement all these things in hardware, it means you have to spend a lot of money. And so this particular method is very expensive. It's instantaneous, no doubt, but it is certainly very expensive, and that is actually it's very expensive. Because, can you tell why it is expensive now? So the number of components required are too many, and they just go on doubling up, you see. So with addition of every bit of your ADC, you have doubling of components required, and you have a more and more complicated combination logic circuit. Of course, it's easy to implement, but it requires a lot of hardware. Lots of hardware is required. So this is the drawback, the main drawback of the analog to digital conversion using the flash method of conversion. But you see that there are several applications where this is already used. Now, when we make use of our CCD cameras, etc., you see, we are interested in obtaining the signal instantaneously. So many different locations, so many locations, every pixel, and we would like to know what is the intensity, which is measured in terms of the number of bits. So we would like to know, depending upon the analog value of the signal, we would like to know exactly what is the digital representation. So all these are done instantaneously using the flash method of analog to digital conversion. Now, because this is very expensive, you can certainly simplify this. You can simplify its usage. You can use it for in a particular combination. You can multiplex it with different sensors or with different channels and use just one analog to digital converter. Okay, so for example, um, you may have a multiplexer circuit. So here you may take a signal. You may have a number of signals. Okay, so I'm just showing one here, and just so we may have a number of signals like this. So we have a number of inputs, number of channels. Let's say there. This is channel 0. Okay, channel n-1. This is channel n. So we have so many channels here, and we have just one analog to digital converter. Uh, you already know its symbol. Let me see if I can take the symbol from, yes, we can take it from here if it's available readily. Yeah, seems to be. So we have this flash ADC. Okay, we'll write it here, but we have only one. So this is a flash. That's because it's expensive. Flash analog to digital